Since we have so many tricks for calculating integrals involving trigonometric functions, we can actually solve a lot of other tricky integrals by turning them into integrals made out of trigonometric functions. The idea here is to sort of use the U substitution idea, except backwards. With U substitution, what we usually did was we had some complicated expression involving x, and we gave that whole thing a new name u. But what we're going to do is sort of the other way around. We're going to replace x with some new function of a new variable. And since we're going to be using trig functions, we'll usually call that new variable theta. But the idea will be the same. Once you have chosen a substitution, you will have to calculate differentials like this, and then complete the substitution by eliminating the old variable and getting only rewriting everything in terms of your new variable, and then hoping that the new integral is easier than the integral you started with. With all that in mind, try working on the problems in this handout on your own, and if you get stuck, unpause the video and I'll see if I can help. Okay, hopefully you've worked on number 1 on your own. So let me work it out, or let's work it out together. So here I'm just suggesting that you use this substitution. So x is 2 times sine of theta. And this isn't an arbitrary choice. So the reason why you might have the idea to use this sort of substitution is the tricky part of this integral is the square root of 4 minus x squared, right? And the 4 probably isn't really the important part. The important part that's making this tricky is just the fact that it's the square root of something minus x squared. So just to sort of come up with this idea for the substitution, let's put a 1 here just to come up with an idea. Well, so we're looking for something, right? The tricky part about this is the square root. Well, the square root wouldn't be a problem if the inside were a perfect square, right? So what we would like is we would like it if 1 minus x squared were equal to a perfect square. And if you just look at this pattern, well, there's actually a situation that we know where this pattern happens, and it's with sines and cosines, right? Cosine squared is equal to 1 minus sine squared, right? That gives us the same pattern because we have 1 minus a thing squared equals another thing squared. So, and what's playing the role of x in this pattern is sine. So that is why that's how you would come up with this idea to use sine in this situation. A little experimentation will show you that if you have a number here, the square root of this is the coefficient that you want in front. So with all that in mind, let's try this substitution. So anytime you do a substitution, right, once you've introduced your new variable, you need to compute differentials. So let's do that. dx is 2 cosine theta d theta. And now we can do our substitution. So unlike with U substitutions, right, you won't really need to do any shuffling around. We can just take these pieces and plug everything in. So integral of dx, so that's 2 cosine theta d theta, over x squared, but x is 2 sine theta, so that squared is 4 sine squared theta, times the square root of 4 minus x squared, but x is 4 sine squared theta. X squared is 4 sine squared theta. All right, so we're done with our substitution, right? We got rid of all of the x's, now we only have thetas. And our hope is that this new integral is somehow easier to do than the integral that we started with. So this integral will be easier to do if, right, clearly we're going to have to simplify this if this has any hope of being easier to do because of this square root part. But remember, the whole point of this substitution was that we turned a messy thing into a perfect square. So this square root will cancel. We just have to do the algebra to see how it turns out. So let's move over here. So first of all, this 2 cancels there, and we're left with a 2 in the denominator. Let's move that out. Also, this square root is the same thing as, right, we can factor out that 4 inside the square root, so 4 times 1 minus sine squared theta. But then we can move it outside the square root. So it's 2 times the square root of 1 minus sine squared theta. So we have an extra factor of 2 here. Let's move that outside. So that cancels the half. Integral of cosine theta over sine squared theta times the square root of 1 minus sine squared theta. All right. Well, remember, the whole point of this was that 1 minus sine squared theta is cosine squared. So this stuff inside the square root is cosine squared theta. But the square root of a perfect square, right, it just undoes the square. So integral cosine theta, oh, I didn't write my d theta here, d theta. Cosine theta d theta over sine squared theta. Now, so the square root of cosine squared theta should just be cosine. Now there actually is something a little subtle here, because really the square root of cosine squared is the absolute value of cosine theta, not theta itself. But in practice, when you're doing these sorts of integrals, usually the bounds of integration will make it so that you don't usually need to worry about whether cosine is positive or negative. So just for the time being, we're going to leave off those absolute values. All right, so these cosines cancel now, and we get the integral of 1 over sine squared, which is cosecant squared. All right, and cosecant is the derivative of cotangent. Actually, I think it's the negative of the derivative of cotangent. So we get minus cotangent theta, not d theta, plus a constant. But, you know, this was an indefinite integral, so we need to get back to the original variable. We need to get back to x. How can we do that? Well, right, trig functions are all about triangles, or one way of interpreting trig functions is that they're about triangles. So let's draw a triangle that depicts this equation. Right, this equation is, it's nice to have the sign by itself, so 2x over 2 equals sine theta, right? Well, sine theta, sine is opposite over hypotenuse. So to draw a triangle with the angle theta in it, to draw a triangle for this equation, we need the opposite side to be x and the hypotenuse to be 2. But then we can use the Pythagorean, this is a right triangle, so we can use the Pythagorean theorem to find the adjacent side here. It's the square root of 4 minus x squared. And now that we have a triangle with theta in it, a right triangle with theta in it, we can write any trig function of theta. In particular, we can write cotangent, right? Cotangent is adjacent over opposite, so that's square root 4 minus x squared over x, plus a constant. And we're done. Right, so this trig substitution idea, it worked out pretty well. It's not too bad. Notice that as you go along, this trig substitution produces an integral in terms of theta that has a bunch of trig functions in it. So usually you will need to have all of your integrating trig functions powers ready to go for these sorts of situations. All right, go ahead and pause the video and try number 2. Okay, for number 2, we've got integral from 0 to a of x squared times the square root of a squared minus x squared, and a is just some constant here. Well, this stuff inside the square root, it follows the same kind of pattern that we saw in number 1, right? It follows the constant squared minus variable squared pattern. We want this to be a perfect square, So we should use sines and cosines again, right? The Pythagorean identity for sine and cosine says that 1 minus sine squared theta is equal to cosine squared theta, right? We want this right-hand side to be a perfect square. We have an a inside, though, so if we multiply this whole thing by a squared, we get a squared minus a squared sine squared theta equals a squared cosine squared theta. So what this is telling us is that, right, in our integral, we have an x in this position. So x should be x squared in this position. So x should be the square root of a squared sine squared. It should be a times sine. So we're going to let x be a times sine theta, right? So general rule here is if you see a difference of squares like this with constant squared minus variable squared, a trig substitution might help. So now we need to calculate differentials. So dx is a cosine theta d theta. And now we can do our trig substitution. When we do this trig substitution, you don't need to change the bounds, but I like changing my bounds. So when x is 0, right, to make sine produce 0, the angle has to be 0. It doesn't have to be, but you know, we should use the restricted domain of sine from minus pi over 2 to plus pi over 2. So in that domain, theta has to be 0 to produce 0. To make this whole thing produce a, theta has to be pi over 2. Okay, and now we can do our substitution. So x squared is a squared sine squared theta, square root of. Now this stuff in the square root, right, we've cooked things up so that we're going to end up using this identity, but let's write it out anyway. A squared minus x squared is a squared sine squared theta. And then dx is a times cosine theta, d theta. All right. Now, let's see, we have a factor of a here and 2 factors of a there. So altogether, that's 3 factors of a, so a cubed. So let's move that out front. Remember, a is a constant. Integral from 0 to pi over 2. We have sine squared theta. Inside this square root, we have a squared cosine squared theta. And the square root of that is a times cosine squared theta. So yeah, a times cosine theta. All right, times this other cosine theta at the end. D theta. All right, so now we have one more factor of a to move out front. So a to the 4th, integral from 0 to pi over 2 of sine squared theta times cosine squared theta, d theta. All right, now since the exponents on both our sine and cosine are even, we can't do a u substitution. We have to use some double angle identities. So I'm going to do it this way. Sine squared times cosine squared is the same thing as sine theta times cosine theta squared. And so inside these parentheses, I'm going to use the a double angle identity. So I get, let's see, a to the 4th out front, integral from 0 to pi over 2, and then this whole thing squared, and sine theta times cosine theta is 1/2 sine theta, sine 2 theta. All right, and d theta. Okay, so now when I square this 1/2 turns into 1 over 4, so let me move that out front, a to the 4th over 4, integral from 0 to pi over 2 of sine squared 2 theta, d theta. Now I need to use another double angle identity, a to the 4th, that's a to the 4th, over 4 times the integral from 0 to pi over 2. Sine squared 2 theta is 1/2, 1 minus cosine 4 theta, d theta. Right? Yes, okay. All right. Now we can pull this 1/2 out front. So a to the 4th over 8 times, and then integrate the stuff that's left. We get theta minus 1 over 4 sine 4 theta from 0 to pi over 2. So we get a to the 4th over 8 times theta, which is pi over 4. And then all the other pieces, sine of 4 times pi over 2, that's 0. And then when we plug in 0, we get nothing but zeros. So this pi over 4 is the only piece that survives. So we get a to the 4th times pi over 32. Okay, bit of a bear, but this trig substitution got the ball rolling. All right, pause the video and try number 3. Okay, for number 3, we have this square root, so definitely, probably you're thinking trig substitution, but it's not a difference of squares, right? If you remember, what made these previous examples work was because there was a difference of squares, this trigonometric identity with sines and cosines was helpful because it let us turn a difference of squares into a perfect square. But that's not the situation here. Here we have a sum of squares. So what we need is some identity that has a sum of squares equal to a perfect square. But there is such a trig identity involving secant and tangent. Secant squared, that's a perfect square, is equal to the sum of squares 1 plus tangent squared theta. So it looks like what's playing the role of x in this identity is tangent. So instead of using x equals sine theta, we should use x equals tangent theta. So because it's a sum of squares, we should use tangent instead of sine. So now we need to calculate differentials. dx is secant squared theta, d theta. And now we can do the substitution. So we get integral of dx is secant squared theta d theta. And then in the denominator, x squared, that's tangent squared. And then square root of tangent squared theta plus 1. Okay. So integral of secant squared theta d theta over tangent squared theta. And then the stuff inside the square root here is secant squared theta, right? That's what this identity up here says. And we're taking the square root of it, so we get just secant theta. Again, modulo some trickiness involving absolute values, but let's go with it. Now we can simplify this, so cancel a factor of secant, and we get integral of secant theta over tangent squared theta d theta. Now what to do with this? Well, I mean, it's kind of hard to know, but one thing you might try, one thing you can always try with trig functions is rewriting everything in terms of sine and cosine. So when we do that, we get, let's see, secant is 1 over cosine, and then over tangent, which is sine, tangent squared, which is sine squared over cosine squared d theta. And then, right, we should simplify this messy rational fraction here. We get, right, flip the denominator, we get cosine squared theta over sine squared theta times another 1 over cosine theta. But then a factor of cosine has gone here, d theta. So we're left with the integral of cosine theta over sine squared theta, d theta. But this is ripe for a trig substitution. Or I'm sorry, for a u substitution because of the cosine theta in the numerator. So we can let u be cosine theta. du is minus sine theta. And then move this minus sign over. So then we get, let's see, cosine theta d theta makes minus du. And then 1 over sine is u. Oh, I've done this backwards. Back up, back up. None of this was right. For u, we needed to take sine theta. There we go. So du is cosine theta, d theta. And now we don't have this unfortunate minus sign. That's nice. And the denominator is just u squared. And so when we integrate, we get minus 1 over u plus a constant. Now we need to undo our substitutions, right? We have to get back to the original variable. Undoing the u substitution is pretty straightforward because, after all, u is sine theta. So 1 over sine theta plus a constant. But now we need to, this is cosecant theta. Now we need to get back to x. But, right, x is tangent theta, and we have cosecant theta. So, you know, it's kind of inconvenient to get back to x here. We could solve this for theta and get theta is inverse tangent of x, and then plug that in here for theta, but then we have a trig function composed with an inverse trig function. That can always be simplified. So we should simplify this right off the bat. So let's do what we did in previous examples and draw a right triangle for this trig substitution equation. When we draw a right triangle for this trig substitution equation, right, we need an angle, so there's theta in a right triangle. X is the tangent of theta, so let's see, tangent is opposite over adjacent. So we need to put labels on the opposite and adjacent sides so that the ratio is x. And the easiest way to do that is to put x on the opposite side and 1 on the adjacent side. So now x over 1 is x. Good. We can find the hypotenuse using the Pythagorean theorem. So that's the square root of x squared plus 1 squared, but 1 squared is 1. And now we can use this triangle to figure out any trig function of theta. In particular, we can use it to figure out cosecant. So cosecant is the hypotenuse over the opposite. So we get square root of x squared plus 1 over x plus a constant. And now finally we're back to the original variable. All right, go ahead and pause the video and try number 4. All right, here's our last one. Here we have a difference of squares again, but this time, right, in our first example where we used x equals sine theta, the minus sign inside of here was on the variable, but this time it's on the constant. So we need a difference of squares where the minus sign is on the constant part, not on the variable part. And we can just rearrange the Pythagorean identity for tangent, right? Tangent squared plus 1 equals secant squared theta. We can just move the 1 to the other side, right? And then we have a difference of squares equals a perfect square where the minus sign is on the constant piece. And then, of course, if we multiply everything through by a squared, we get a squared tangent squared theta equals a squared secant squared theta minus a squared. And now, right, we're set up now for a trigonometric substitution. Now we see that for x, we should take a secant theta. That means dx is going to be, let's see, derivative of secant is secant times tangent. So secant theta, tangent theta, d theta. And now we can do our substitution. So integral of dx, which is a times secant theta times tangent theta, d theta, all over square root of x squared, so that's a squared secant squared theta, minus a squared. All right. So integral of a times secant theta times tangent theta d theta over, and then according to our identity here, the stuff inside the square root is a squared tangent squared theta Okay, now we can simplify the square root. Integral of a times secant theta tangent theta d theta all over a tangent theta. And then the tangents cancel. The a's also cancel, which is nice. We're left with just the integral of secant d theta. And that's one that usually we'll just look up, right? It's natural log, absolute value, secant theta plus tangent theta plus a constant. But as usual, we need to get back to our original variable, the x's. So to do that, we can use this same right triangle trick. So let's isolate the trig function here. So we get x over a equals secant theta. Now we'll draw a right triangle. So right triangle that has theta for one of its angles. And we'll label the sides so that secant of theta actually is x over a. Secant is adjacent side over, no, it's hypotenuse over adjacent, sorry. So the hypotenuse should be x, the adjacent side should be a, and then we can find the third side using the Pythagorean theorem. So it's the square root of x squared minus a squared. And now we can use this triangle to write down, to evaluate these trig functions. So natural log, absolute value, secant theta. So secant theta is hypotenuse over adjacent, so x over a, right, which really is just the substitution up here, plus tangent theta, and tangent is opposite over adjacent, so square root x squared minus a squared over a, plus a constant. There we go, we're done. All right, one last here, so pause the video and have a go at it yourself. Okay, so for this one, finding an average value of this function from 1 to 7. So remember, the average value is just the integral of the function, but then you have to divide by the length of the interval, and 7 minus 1 is 6. So integrate from 1 to 7 and then divide by 6. So 1 over 6 times the integral from 1 to 7 of square root x squared minus 1 over x dx. And now we have to work out what should we do with this integral. Well, the square root, right, with the squares inside should make you think of trig substitution. So then the only question is, which trig substitution? Sine, you use sine when you have a constant minus the variable squared. You use tangent when it's a constant plus the variable squared. You use secant when it's the variable squared minus a constant. So we're going to use secant. And remember, the constant, so we're going to use x equals some number times secant theta. And this number in front is always just the square root of whatever is being subtracted, right? For all three of these substitutions, if you have a number other than 1, the square root is what goes in front here. So square root of 1 is 1, so we just have a 1 here. Dx is secant theta tangent theta d theta. And now we can do the substitution. So 1 over 6 times the integral of. So with these bounds, I don't think it's going to be very informative to try to translate these bounds to theta values. It would just get messy. It'd involve some inverse secant business. So let's just leave these as x bounds. At the end, when we need to plug these bounds in, we'll need to convert the function back to the variable x before we can plug in these x bounds. Okay, so now we're going to integrate. So denominator is just x, which is secant theta. In the numerator, square root of x squared minus 1. But remember, so this is going to be secant squared minus 1, but that's tangent squared, and the square root of tangent squared is just tangent. Okay, and dx is secant theta tangent theta d theta. Now our secants cancel, that's nice. So 1 over 6 times the integral from 1 to 7 of, looks like we have tangent squared theta, d theta. All right, so tangent squared, right? We need to use all our tangent secant integration tricks. And since it's tangent squared, we can turn those into secants, and we'll have a constant term and a secant squared term. And we know the integral of secant squared, so that sounds like a plan. So we'll use the Pythagorean identity to rewrite tangent squared theta as secant squared theta minus 1 d theta. So 1 over 6 times, so integral of secant squared is tangent theta. Integral of 1 is theta. And this is from, remember these bounds are x values, so from x equals 1 to x equals 7. So if we aren't willing to translate the bounds into theta values, we have to translate back the thetas back into x's. So 1 over 6 times tangent of theta, let's see, so we need a right triangle for that. So if secant of theta is x, so here's theta, so to make secant of theta be x, we need an x on the hypotenuse and a 1 on the adjacent side. So the opposite side is square root of x squared minus 1. So tangent in this triangle is just the square root of x squared minus 1 minus theta itself. Well, to get theta itself, we have to use an inverse trig function. There's no way around it, really. So we could use inverse secant, but inverse secant is a little bit troublesome because A, it's unfamiliar, B, if we go to get a decimal approximation for this value, most calculators don't have an inverse secant button, so let's use cosine instead. Right? Using this triangle, cosine of theta is 1 over x, and that means that, let's see, taking inverse cosine, we get theta is inverse cosine of 1 over x. So theta is inverse cosine of 1 over x. And this is from 1 to 7. And now we can plug in our bounds. So 1 over 6 times, this is going to be a mess, square root of, let's see, 7 squared is 49, minus 1 is 48, so square root of 48. This square root probably simplifies, but let's just leave it as square root of 48 for now, minus inverse cosine of 1 over 7. Okay, minus, now plug in the bottom bound. Let's see, square root of 1 minus 1, so 0, minus inverse cosine of 1, that's also 0. So this last part is just 0. So there we go. We get 1 over 6 times square root of 48 minus inverse cosine of 1/7. So that's the average value of this function on the interval from 1 to 7.